All right, well, welcome to today's Q-Box seminar. It's my great honor to introduce today's speaker, Professor Dragan Mihailović from Slovenia and from the Stefan Institute from the University of Indiana. And I met Dragan, I believe, in 2018 at one of the Gordon conference, if you remember, and his work has been very inspiring for a lot of my early work on a range of materials, and he has been a true pioneer in a lot of time-resolved complex spectroscopy on different. And in the past decades, he also kind of switched direction a little bit after the discovery of a very interesting phenomena in one of his favorite material, tungsten disulfide, where he discovered a transition to an inner state accompanied by an insulator to metal transition after turning just a single light bulb. And ever since, Dragan has pioneered a lot of work about understanding what this thing is and actually trying to make this a quantum device. And really something to talk about using a variety of different techniques he developed in the past decade. And Dragan has won a lot of work, and I will probably not to spend half an hour reading out loud, but among different prizes, he has won the Patriot Award in 1987, and in 2002, he was awarded the Zayas Prize, the highest award outstanding achievement in science in Slovenia, and he's also held two ERC grants, and also is a member of the Slovenia Academy of Sciences and Arts and the Slovenian Academy of Engineers. And I guess without spending really the next half an hour introducing Dragan, let's give them a warm talk.
Yeah, thanks very much, Alfred, for the introduction. And most of that just shows is a sign of age. So don't worry about that. Or it comes with time. So, and I really appreciate this forum just now. I think the average age is very nicely low, and that's really makes a great it's great motivation for this talk. So, as Alfred said, my general outlook on quantum materials has been through the eyes of somebody who's doing pump probe experiments, of ultra-fast experiments. I think the first one I did, 1983. Needless to say, it was not successful. And so, but I stuck to that, and eventually this was a very productive field, especially in superconductors. But in the last few years, like Alfred said, we found some kind of fruit fly with quantum materials. I'll tell you a little bit why that's such an interesting material. But there's one aspect which is particularly interesting, and that is that as a quantum material, when it goes through sequence of events in self-assembly, let's suppose you start with a Facebook. I'll get to that in detail in a second. It's not always going to end up in the same state. You know, we typically, especially when we discuss things directly, we discuss them in terms of ground state, type of state, and then we go from the type of state. The ground state, we don't really consider that this ground state may not actually be homogeneous, may not be. Very often we don't end up in the ground state. And one of the good examples is, of course, everybody knows by now, is our own universe, which is apparently not a ground state. And so the question is, should we typically people draw a potential like this for the universe, and we are here, a metastable state, and that's the end of the story, and we're discussing tunneling events into ground state. But there's a huge amount of life in this universe that we live in. We are here, all this stuff, right? I mean, this is actually the motivation. So what I'm going to address is one particular example of some self-assembly in the quantum material, which gives rise to noise. So basically, this is the noise of quantum self-assembly. There's an alternative title to this. Let me see if this works. Yes. Okay, good. Now you can see that, right? Without noise. And this is the experiment, and the experimentalist made it. And this experiment, when it was done, we were really fascinated by various aspects of it, including some quantum aspects, and a lot of people that I just talked to were very interested. So that this talk contains a lot of input from some very famous people like Duncan and Anton and Alexei and so on. So, okay, noise. I'm going to start off with just a few slides of background on noise in general, in electrical systems, quantum systems, for example. So it was interesting when they invented the vacuum tube, they thought it would be noiseless. Well, after all, it's just vacuum in there, right? I mean, you've got electrons and vacuum, and you know that. Of course, that's not the case. The importance of noise is illustrated by the right-hand picture. Of course, the T1, the station time in the quantum processor, the superconducting front the machine is about 150 microseconds, and it seems to be a great news event when they find some noise mitigation. Right, so this is the event was last year in December when this paper came out by Google on the Willow processor. They found that there's an error correction algorithm that it's actually an important milestone, but the effect of that was in dollar terms given by this number. Okay, that's the stock went up by that much market capitalization. So it is an important topic, and it has been so for a long time. So let me continue. Another aspect is, well, this is something that we probably all know. This is the story of pigeons in the horn. And so that again is a measurement of noise. Right? And now I was really pleased to see this panel up there, which is actually the same thing as I'm showing here, you know, at the entrance. And my point here is what these measurements are noise. Okay, but the astronomers have a great advantage. They can point their telescope to the noise, and then they can identify the noise just by pointing in the right direction, right? So this is somehow, but the point that what you see here is that in different regions of the spectrum, the noise is different. So they are actually able to get a map of the noise. Different side pattern. All right, so we'd like to do that, let's say, in a quantum processor or some device or quantum material. So this is not this example. Now, going to the theoretical background, it's actually interesting to find that Albert Einstein discussed noise, electrical noise, when he was deriving the equations for the random motion. But he thought that it could never be measured, so he didn't bother finishing the calculation. This is find that in some notes. So the actual breakthrough was done by through the Hans Lorentz, the Haas, of course, the Haas and Lorentz are also well-known physicists. She is somehow related, but she derived the mean square value of the current. So. And of course, we all know about Johnson noise, which is nothing other than black hat radiation. Noise is really big. Right. In practice, noise, there's some puzzles in noise. One is that it always seems to follow this 1/f. Right? But the question is why? And that's been a puzzle for a very long time. And maybe an interesting aspect is that sometimes you can recognize why there's a particular peaks in the noise. So when we consider Brandenburg's Brandenburg concerto number 1, like this. It's an F major, and presumably these peaks correspond to F. Okay, and hopefully, otherwise it's out of tune. Okay, so that's the these are experimental observations. So let me go on to a more down to earth thing. So in devices, in many different kinds of devices, noise is a problem. If you're buying, it used to be the case, if you're buying a hi-fi for your home, you know, the noise characteristics and something virtual, actually. Whatever, the noise is it. So the electronic noise is it, as I mentioned, that's key. Typically, what one does is one has this kind of contacts. This is recent work on this material, which I'll talk about today, mainly by Alexander Baladin. Two contacts, a bit of a sample, and you measure the current, and the current has these fluctuations, which are not random, the so-called telegraph noise. And okay, what you see here is the Fourier transform of this noise of this time series. We see sometimes that it keels over low frequencies, and this is shown here more accurately or more identified. And you see they fit this to Lorentzians, and therefore, which implies a Lorentzian implies that you have a two-level system. I'll show you why. That means that you have a specific source of noise. Okay, in this measurement, there's absolutely no hope of determining where it comes. Right? It's a microscopic measurement. You measure a current, it's hopeless. All right. Now, let me just give you a little bit more basics on noise. If you have a two-level system, like people are discussing in organizations, for example, if you couple it to an environment, you get like exponential decay. With your physics, early physics derivation. Fourier transform of that, of an exponential decay, is a Lorentzian curve as a tail which goes as one square. Okay. However, if you have many such oscillators, like down here, and you integrate over all the different two-level systems, you could essentially get one over. So that tells you that it's really probably pretty hopeless to determine what the source of the noise is, right? Experimentally. Let me move on to something that's a little bit more interesting, at least in the title quantum noise. This discussion, which probably ended with this paper or soon afterwards, essentially, if you have a quantum system, the question is, do you have quantum chaos or not? Of course, proper quantum chaos is not something we would like to consider, doesn't exist, but you can have chaotic approximations in quantum systems. And so there is something called the quantum chaos. There's a whole field, in fact, discussing this. Now, the main point, there was a theoretical paper which says that, in fact, a chaotic orbit is such a noise which goes as 1 over f. So it's similar to a single trajectory or single two-level system. And you may intuitively actually understand. Sorry, it's 1 over f squared. So a single orbit goes as 1 over f squared, and a chaotic orbit is 1 over f. That's the bottom line of 20 years of papers. However, you can also understand that easily, intuitively, that if you average over many such single 1 over f squared, as I did in the previous slide, you get.
Probably need to unlock.
No. All right, locked. Sorry about that. Okay, maybe I should press the button on it. So yeah, it's a trivial point. If you have many such 1 over f squared, an average over them, you get something that looks very much like that. So from an experimental point of view, again, it's perfect confusion. We really don't know what. So you need to do something. So, now let's look at the real system. So let's try and make a quantum computer with some superconductors or aluminium oxide, and some smaller places of typical convention. And this is made under different conditions, and you can see it's part of our deal, and all these things here In this, shown by the arrows are sites where you could have trapped electrons, and those electrons have rattle around and do the noise. Okay, so but that's all just I mean plausible, but how can you measure that? So and it's indicative that actually all these processes today have so let's take IBM for example. This is their marketing page. All the processes that are currently used, but what you see here is that they all have similar T1 of the around 100. And the reason is they all have the same problem, right here. All right, enough of that. So let's go back to our fundamental problem. So we are interested in self-assembly of quantum systems after we perturb them. Now we want to do that experiment because we want to start from a well-defined point. So let's suppose we start with the ground state, what we call the ground state of the system, which is nicely uniform. Now let's suppose that that's a depiction of that. We shine a laser at it, we destroy the electronic order. We are going to study electronic order. We could also study magnetic order, but the method that we use doesn't work so well. So we're going to look at electrons. So only electrons, don't worry much about the lattice at all. So the electrons will try and order, so we have a lot of disorder for a short time, and then they start to pile up and self-assemble. And during this process, there may be some external influences, such as more light, more pulses, or lattice heat is supplied, or no, which is time dependent, and there may be strain and so on. But eventually you end up with something which, if this is a metastable state, then you end up in a different order state than you start with. Right? Now, usually we don't consider that. Actually, in most experiments, on most facilities, we have a simple problem. That is that most of the experiments that we do average over time and over space. So bump probe experiments, SLAC, any accelerator that you consider is doing measurements stroboscopically. Do excitation, and then you have a time delay, and average over multiple events that you have created by the first one. So if this is a phase transition, you basically average it over all the possible outcomes. So imagine that you had a big bang and somebody was planning experiments in this, and so they would average on all the possible universes that would come out after the big bang, right? And that's the type of measurement we have been doing for 40 years. Right. So what we're looking for, actually, in my work, is the details of individual outcomes of patients. So we try to do that. So this is the conventional stroboscopic techniques down here. If you have a metastable state, so your minimum should be long that you can use steady state technology, then you can do a lot of experiments. That's where we are. So we are looking at the metastable states in tantalum sulfide, which I'll show you in a second, and it will live for low temperatures very long enough to do, for example, tunnelings or STM microscopy or other types of microscopy. Okay, so now the important one more aspect is that in this region of time scales, so these are typical femtosecond microscopy. On this region time scales in between, there's very, very little data. It's surprising, but it's almost completely absent in any kind of quantum material. Magnetic or not, or charge order, or phase transition. Simply because there's no technique. Nobody has the right way to. So there's two things. There's not only a time movement, but also a spatial problem. That typically most techniques that we use at this end here are K-space, which means average over K, right, or over space. And that again doesn't tell you about mesoscopic homogeneities that may be occurring in this process. Okay, like that. Right. So I'm gonna discuss mainly traditional initial dipole progenites. These are layered materials like so. The particular one I'll be interested in is tantalum disulfide, which is there's a nice crystal here, which is grown by my younger colleague. And but the material belongs to the family of compounds which have electronic superlattice. Now, what I'm showing here is the superlattice orderings for different filling factors. So, for example, F is the filling factor here. If the filling factor is 3, then you have a superlattice structure like this. Filling factor is 4, or a quarter, I'm sorry. 1 every 4th site is filled by an extra electron. Then the superlattice looks like that. If it's 7 or 9, 12, or 13, 16, it goes on to 19, 21, so forth. And it's just all these F's are given by this geometric rule. That's just pure simple geometry. All of these compounds actually exist. Right? So that's the remarkable, how should I say, insights that one gets just by drawing simple geometric pictures. Okay, so we're going to look at tantalum disulfide. Now, the reason we're looking at that is this discovery some 10 years ago. That if you shine a short laser pulse onto a sample of tantalum disulfide, which has 4 fabricated contacts, you find that the resistance of that material drops by 3 orders of magnitude and stays there. So that's the experiment shown here. So the resistance normally follows the Wood curve. I won't get into the details why. You don't really care just now. But if you shine a single laser pulse here, it drops down there, and then when you warm it up, it recovers the original state. You can do this in any number of times. This effect was actually not discovered in resistivity. You weren't in the habit of making contacts every time you did control. But it was discovered in the coherent mode spectrum. Now, coherent mode is essentially the mode which describes the oscillation of these electrons coupled to the lattice, like the phonon, and that it corresponds to the ordered state. And the peculiar thing was that, so that when I was just one day, and a student came out of the lab, the coffee room, and they said, "I'll burn the sample." And but he was supposed to do power dependence, fluence dependence of this oscillation. And so I asked him what was the fluence, and he said, "1 millimeter." And I said, "No, it's much, much too low." So that was actually the beginning of everything. I told him to go back and measure, and lo and behold, after a while, they found it actually destroyed the original order, which is this is the 1/13 order in this material, and created something which looks okay. So that's the origin of this interest in this material. Now, there's an important. I need to give you a little bit of background physics on this material so that you can understand why these phenomena actually occur. And that is perhaps the most obvious thing is that the band structure of this material has flat band around the gamma point. But the implication of that is that electrons are slow. They're slow. They're very strongly coupled to the lattice, the large mass. And that means that essentially they're prone to localization. And this is a scenario where if they have very low kinetic energy, then what else is there? There's Coulomb energy. So Coulomb energy is important. Coulomb energy is dominant, of course. Dominant effect. And that suggests that the material is prone to the formation of corons. So this is basically the idea that already before the Wigner, when we have the dominance interaction with Coulomb, it will actually crystallize. Okay, so we form crystal electrons. And in this case, we are dealing with polarons, not with bare electrons, but that's basically the same. Now, I won't go into the detail. This is a justification why this is reasonable. But I'm an experimentalist. I really believe things which can be unambiguously measured. And this is one nice experiment, which is kind of a. The point of this experiment was to see if these polarions actually exist, could be measured. Right? Basically, lattice distortion around the length. And it's a pair distribution function measurement of X-rays, which measures the interference between two atoms of different distances. Let's see what's involved in this. So the bottom line of that is that at high temperatures, when none of the ordered states exist, we still see we clearly see the evidence for polar lattice distortion. These lattice constants around an electron are somewhat distorted on a scale of 1 nanometer. So basically, there's an object there which has a signature which gives this wiggle here, and that's just interference between zone positions, which exists well above any temperature where there's zero orders. And then when it goes down, these polarions order in different ways, and that's the physics of the video. Now, there's an additional twist to this story. So there's still a bit of doubt. Maybe this is from something else. Well, there's a beautiful good nature. Sometimes, if you're careful enough, you're lucky and you find it. In this case, turns out if you heat the sample to above 700 degrees approximately, it starts to change structure. Starts to take structure in such a way that one layer remains the same and the second layer changes to a different polytype, just slight structural modification. You get layered. One. Sorry. Each layer is different. And lo and behold, the amplitude of the signal drops to exactly half. Okay, so it's not often that you're lucky that you can really claim something with such degree of certainty, but in this case, nature is quite helps. We're grateful. So, okay, let me move on. If you just now, I'd like to introduce you briefly to a model, which is a basic, very, very simple model, which is using the fact that we have both polarions and they have very low kinetic energy. So we essentially set up a Hamiltonian which only has Coulomb. And it's screened, okay, so it's not on site only, there's some screening damage. But the main point of, so there's the Hamiltonian, it's about as simple as you can possibly get. And here's the screening. And if you just change the filling according to this formula that I showed you earlier, you get all sorts of different states. At 1/2, 1/3, 1/4, you start to see the main laws. This is a Monte Carlo calculation. At 1/13, this is the material we're interested in, but also 1/7 and 1/21, etc. So these are all the ordered states that you can get just by changing the filling, nothing else. And on the right, we have a list of materials which follow all these magnitude fractions. So that's actually important in predicting phase diagram. Now, some of you might be familiar with various phase diagram quantum materials. The difference here is that this is very extensive. So we have to go from a filling of 1/3 to 1/21. So the density of electrons increases in this direction. And tantalum disulfide is here. And this is the more conventional phase diagram of most materials that you're familiar with. Maybe a hot state here and something pseudo-gap state. Superconductivity is generic phase diagram. So that's only a small portion. And in our experiments, so this is the first result that I'll show you from STM imaging. So what you see here is tip scanning SCM2. And so we shine a sample. This is the radius of the spot, or the elliptical laser spot. And we can, just by one shot of laser, we have a lot of different cases to consider. And all these experiments are each little, this, don't forget the scale, this is 200 microns. STM, we typically look at 3 nanometers. So we have a tiny bit square here, and we have the option of examining different fluids. And in fact, you get, as a result, you see a different set of different states. Now I'm going to talk about that tomorrow at the seminar in more detail. Here, I'm only interested in this state. Okay, as an example. So this is the original state, simulate with pulse, you get that. Okay, and what you're seeing here is polars, individual polars, white blobs. Okay, so next experiment, and this is where the fun starts, is to use very fast scanning. Yeah. So rather than use a conventional STM, we decided to speed things up a bit. So this is 10 to the 4 times faster scanning. It means that the tip is scanned across the sample in a sort of a swinging fashion with a very fast rate. Each point is sampled at something like 100 megahertz. So then we have basically construct a movie. And what you're seeing here is the surface of the sulfide crystal, which has the main wall here. I'm not sure if you can see that, which is sort of moving left, right. Now, I generally show images which are completely unadulterated, very raw data, and very much against. I mean, editors who complain that the pictures are not good enough. They prefer pictures which are massaged to the point of artificial. Not to be, I mean, such a question. So what you see here is, I'm not sure, it actually maybe I see it looks better on that one. You see a domain will fluctuate. Right? Now, the way this was, so this machine is actually capable of atomic resolution. So here where resolution is reduced in order to increase the speed of scanning and the area. But what you see, and the stripes across this direction is artificial due to the electrons. That can be, it's a peak. Cut it out in Fourier transform, it just disappears. So in the next slide, I'm going to show you another example where we've done that. Well, this is the one I'm going to talk about the rest of this talk. So what we see here is essentially individual electrons. That should not to worry you. Motion of individual electrons on the real time scale. This is real time movie. Okay, on time scale, which is per second or milliseconds, and we're applying it to image this. We're using a current of 1 nanometer, 10 to the 11 electrons per second. So how are we imaging single electron motion using tip through which tunneling occurs at with 10 to 11 electrons per second? So this is maybe we have a question. Where to start? Well, let me help you with. So what we are actually observing is a trap here, which is formed by one domain here, another domain, you see a domain wall. And then if you look carefully, oops. Press the button for a second. Right. What you see here is lined electrons like that and lined with. So there's a chirality, in-plane chirality domain wall. And so what you're seeing, where the motion is in the space in between these domains. Okay? And the main structure is something that's microscopic. Essentially, it covers the whole crystal. So in the end, you are looking at here, quantum measurement. However, the image you get is a classical one, of course, but the dynamics behind the motion is all the probabilities for finding particular electrons in certain positions is done by quantum processes. And essentially, we have a highly entangled here, which is trying, so the electron here is trying to decide whether it belongs to this domain or this domain or that domain. And it's the fluctuations. So this motion, if you, I don't know if you can see this, but it looks somehow like this motion, the circular motion. Question is that could be if you had imagine that you had some kind of acoustic wave oscillation that thermally induced. That's causing this. So that we can actually test for that. Let me show you how. So here's the raw data again, same movie. So the question is, do these things correlate? So here's an image, which is just an average of all these images. The motion is over here. Here is a picture showing the displacements of each individual electron. Frame to frame, and it's moving. The whole thing is drifting. You see, so this is the drift going from red. Okay, so the whole image is slowly drifting. Again, data has not been adjusted really. So what we're going to do is look at these the dynamic part, and classical motion is simply some kind of displacement like this. Whereas quantum probabilities would, on the other hand, look like that. Simply, each time you do a measurement, you see a position that's essentially increasing or collapsing the wave. And so here's the answer. So we measure a time series of displacements here. We're looking at this point and this point. Nothing should be happening here. So this is time, and this is the displacement. You see it's sort of random, it looks like that. Here, so we're looking at these 2 points, the displacements of these 2 points. So if it's classical motion, you expect to see something correlated. We have one side and the other side. This is two time trace. If there were a correlation, we've already seen this in time trace. There are gaps here because there's still the electrons just not there. But you don't. It's not obvious there's any correlation. In fact, if you don't make a correlation plot, it looks good. So there doesn't seem to be any correlation to the motion of electrons, which are one next to each other. That's exactly what you read.
I'm curious, does it depend on the frame rate, whether you're looking at the aliasing that, or does this motion is acting on the 6 Hz or 7 Hz time?
We've changed the rate, and it doesn't seem well, but not sufficiently large range. Now, an aliasing effect, I think, would look different. It's a good periodic. This is not periodic. So I think that's probably the best, most amazing. But certainly, aliasing is an issue. We looked into it and somehow decided it wasn't relevant. Okay, let me just move on a little bit towards noise. So if we go now, we can go and select particular points on this dynamic moving and look at the noise. And what we see here is different traces of. Sometimes you see a pretty straightforward looking noise, and sometimes you see this called telegraph. And depending on which point you are here, and this here's 400 seconds, many hours. And if you do a Fourier transform, Lorentz fit, you find that there is a single oscillator for one particular site. Next site, you may or may not get in the dynamical region. it's typically behavior like this, so you get some, and of course this looks like 1 over f squared in the tails, as we would say. And that suggests that you have a single peak, essentially. At that point, it's probably driven by temperature, because the ambient temperature here is very high at 7% Kelvin. So it's way beyond the fluctuation regime, this material. Frequency that we're observing, which is 0.1 hertz, let's say, estimate, that corresponds to an energy of 2.14 eV or 10 Kelvin. So that should also pose some doubts in your mind. How is it that we have a two-level system spacing at the minus 10 Kelvin? And it's not completely washed out by 77. Well, I mean, the great thing about this experiment is the data are incontrovertible. It's just a move. Nothing, we've done nothing to it. We have to, it's take brain power. The rest is just brain power. So what we're doing here, so what we're actually saying is that, well, it's some kind of a microscopic effect, but the microscopic fails. Prevent your, it's a bit like error correction in entire qubits, which prevent this qubit from decohering. So here we're tying it to the whole domain, the different domains. And the domains themselves are actually have some topological, non-trivial topological array. So let me just move on a little bit. In the experiment, if we now look at many of these points and plot them just on top of each other, and this is the original fit to the oscillator, you see it's sort of okay. But then if I add them all together, that's the same as averaging, right? And I get 1 over x. So, yeah, pretty simple textbook behavior. Now let's look at the points that are moving. Well, here you see at this region, it's sort of probably more or less 1 over f. Certainly, there's no flat top to fit over into. And this is pretty flat. Remember, this is long scale, so this looks longer on the side. Noise is low. So essentially, what we're saying is in this region here, the noise is very different. We're identifying the source of noise, basically with a topological solution. Now we get what we did next is to analyze this whole array. Previously, I just had selected points. I do all the points in the image. So here it's 400 seconds. It's going like that for each pixel, and from that I can actually analyze the noise components on the entire image. So what starting from this image, I can fit the different components. Of course, this is the problem with this fit is remember, I'll show you this. The problem is that we don't have many points. The Lorentzian fit is not very good. It's strongly weighted by this part. Yeah. Strongly weighted by this part. So we prefer to actually fit the 1 over x squared. It's a little bit more. So here's the result of the fit. It's just, well, here's one oscillator, here's one oscillator. But here's a bunch of oscillators. Notice that they don't actually overlap. Neither does the white noise. Everyone seems to appear everywhere, but generally in this region. So that it's very difficult to understand. Okay, but the main point that I'm trying to make is, well, this is a system which is where we've actually identified a particular atomic site and the sources of the noise. Now, let me go back to some modeling. Now, in trying to understand this, let's start with that model that we had before, Coulomb charge lattice gas, and we add 1 electron. The effect of adding 1 electron is to introduce it spreads out over many sites. The blue means it's more charge, the red is less charge. In addition to this object, there's also there's some topological weakness here. These locations here. Well, this is a heptagon and a pentagon. Pair of those. If you add 2 electrons, you see something gets bigger. You add 3 electrons, it's gone. You get a network. If you take ion, it's 6 electrons, it's essentially the main one. And also the defects seem to disappear with larger number of units. Now let me introduce the concept of fractional charge in this experiment, in this calculation. The fraction here is just the amount of charge enclosed within a Wigner site cell defined by the. Okay. So if we look at these numbers here, put them on the same denominator, they add up to 1 or singular. Okay. So there you get charge fractionalization, and not only that, it's strongly entangled. How can you take out 1 electron? Hard to imagine. In other words, the charge is strongly entangled. That's not science fiction. It's actually just, again, experimentalist. If you prove things, here's an experiment to do that. So we have 3 STM tips. We pass the current from here to here. The effect of the current is to inject electrons, right? So we start from this state, intentionally defective, so we can identify the position in subsequent images. And what you see here is after a single pulse of charge injection, you start to see the main walls. And after further pulses, you start to erase it thermally. And the main walls start to disappear. This is a Wigner-Seitz analysis of that. What you see here is pretty much what I showed you in my picture. You see entangled state here with pairs of defects. And these like to annihilate in pairs. So for example, here the 90 is an example. 2 pairs which have equal opposite Burgers vectors. Right? So green, red, orange, green, orange. So these annihilate. Following all topological rules in the textbooks. Okay. So we can do that now. We're in a position to do a charge elastic gas simulation for the trap that we constructed. So that means we set up left, right, parallel of phase. So this 2 different domains, and this is the 3rd domain. So that's a corresponds, and this is fixed here. Okay, so all the sites at the edges are fixed, and then we let this thing. Do it again. Okay, the energy fluctuates as this configuration or state. So basically, each one of these images corresponds to one particular state of the entire system, not a single electron movement. In other words, this is a strongly entangled system with strongly correlated charges, which are essentially following the dynamics of due to the excitation, the thermal excitation. Now, again, now this is maybe that answers this question at least partially why this is so slow. Okay. Maybe. Okay. But anyway, just to do a little bit of summary here, the oscillation frequency, as I said, is milliseconds or so. Energy scale is 10 Kelvin, eV. Ambient temperature 77, and however, if we do an experiment where we measure the activation energy to go from the main state to the ordered state, that turns out to be zero, and that actually is consistent with the time. This is an experimental plot, which I can't go into, but essentially it seems to be consistent. So Let me just go a little one step further in the analysis and look at the topological defects. We're claiming that the topology, the state is locked by the topology of the adjacent main walls, which cannot be topological objects. So let's look at the experimental dynamics. So what I'm doing here for this plot is showing these dislocations, like I did in the previous calculation. So, and let's do now again, show the calculation. So this is the same. I'm sorry, the images are a bit converted. But here we are. You see, this is frozen, but the main walls have these dislocations. So we're simply not wanting out of calculation. The only thing that's special about it is it has the boundaries. Okay, and the next thing is, should we expect correlations? It's not an obvious question. I don't think I'm not prepared to say that we have a full story. The reason is the following: if we do a Monte Carlo correlation plot, basically from the calculations that I showed you, try and see if there's any correlation between two sites, and we get something which essentially we get no, which actually is a little bit surprising because, at least in some sense, you can imagine that if you have two electrons next to each other, there should be something preventing one of them getting closer to the other. So that's very trivial. But it doesn't seem to be here. Now, the question here is quantum or classical? Of course, it's calculations. Well, is classical, but the Monte Carlo method is driven by random fluctuations, and random fluctuations, of course, are quantum also. So, in some sense, there is some degree of quantumness which is summarized by the Monte Carlo method. Okay, now to really make things awkward, let's just consider a really classical experiment. And so we have a ball with a famous field between two crystal plates, like taking a picture like this, shaking it, and you see all the veins forming here, and you see all sorts of objects appearing for no kind of reason. If I do something more drastic, that is, I tilt this plate, this contraption vertically, so gravity plays an effect. It's effectively the same as applying a strain. See what happens. You basically jam the system, get a glass. I wish I could bring this with me. I don't think they would allow me to play me that. It's pretty fun to play with. So if you have the chance, make one of these. You can play with the distance between plates. That could tell you a lot of different physics. And if you, it's an interesting twist to this. If you make this a triangle, boundaries in the triangle, and these are all 3D printed. So you make different shapes and make circle shape, boundary condition. The effective boundary conditions on the ordering of classical balls is amazing. They're all sorts of things. So the message here is that if you have a quantum system or a classical system, the boundary conditions and the way you apply them eventually determines what you have. So this is a very important message for. I think the great thing about that is that it implies that there's a lot of people don't get understand. Right? It's a huge playground for various states which are reached by choreographed by symmetry, by topology, but also by the boundary conditions, which can also be temporarily and spatially changed. So this is a field which we're all, I think, looking forward to. So let me finish off with this experiment. So this is actually, now talk about classical, this is one. So what we're showing here is conventional STM images of the decay of such a domain state. It happens at a long time. It's many hours. This is very slow. And you see the same as expected, the main was gradually annihilated. Right? And they plot this dynamics in terms of something called the Hamming distance, which is basically the difference is how many of these polarized move from frame to frame. It's ITD, we call it. And this is what you get in time. So what that is signifying is essentially going from one configuration, next configuration, next configuration, so on, in this kind of funnel. So going from that's the ground state. These are all the possible states, also for our little dancing electron. Now, the temperature dependence of that is indicative. It shows that there's no temperature dependence. Low temperatures up to 20 Kelvin, this region here, and then it shoots up to an array and energy, essentially like that, and that's what we like actually. A few slides ago. Okay, now it's a perfect system for simulation. Now it's quantum, so we use D-wave simulate that. And here there's a caveat. If you read the fine print, we use a manual for D-wave picture. It says it's here's down, it's whatever. Okay? 100 seconds. Beyond that, it's noise. The noise says. Okay, so the question is, in our experiment here, do we have are these fluctuations which are driving the dynamics of the temperature, or is it just ambient noise? We're back to the importance. The answer is we cannot tell. The D-wave calculation is set up in such a way that each one of these polarons corresponds to is essentially mapped on a square lattice. Essentially, we have a triangular lattice on the D-wave processor. There's 2,000 qubits on there, and let the whole thing hold with a Hamiltonian, which includes a transfer field. So that this part here is the same as before. This is transfer field term. And once you look at the dynamics of that, you cover a very similar set of pictures. And your rate as a function of temperature is indeed crossover between the oceans. The scaling between the experimental agent and the D-wave, just the difference in the energy gaps. Qubit level spacing. One of them, the other one is off. It's no other scaling range. Got two curves all on each other. All I'm saying is that natural processes driving, one over F processes are driving both systems. In other words, there is a doubt is here as well that this is a quantum process, or rather, it's quantum tunneling, but it's driven by noise, just like the quantum process. Okay, which is set of images. Now, this is another example. Right. So here's my take-home message. There's a lot more complexity to be discovered in our experiments. I think what we desperately need is new methods for looking at this intermediate range of timescales and mesoscopic orders, which includes very non-trivial domain dynamics. Not only domain dynamics, but also dynamics of particles, which are essentially reducing your Hilbert states to level systems. So I think the great thing I really feel very comfortable about is there's nothing to lie about. It's an experiment. It's there. You might not like my interpretation. The experiment is incomplete. It's a raw data.
I will start with questions. Oh, so, yeah. Yeah, I got a technical question like this. So, we said the image drifts over time as well as the image does, and so you're parking the tip at every pixel to measure time series. How do you know the variation of the
I'm measuring frame by frame. Each frame is separate. So I take pixel number 1, and in frame 1 and frame 2. That's the sense. But I'm not parking the tip.
So you do need to register over time.
They're automatically registered. Right? The whole, essentially, all you see is a very slow drift. Now, it could be what you're saying could be give rise to a systematic shift. So drift would basically be
right.
So, what does it mean to use is topologically?
It means that the relation, the structure of the domain walls is defined by their topologies. The direct topology in the following. The domain wall, which you cannot get rid of unless you or you have find an answer. When you have junctions, that becomes highly non-trivial. Because there's, in this case, if you think about it, this is a supervector. So if one electron and the next electron have many different possible positions. Not only the one that's found by the dimensional supervector, but also two different domains have the same. So the concept or the idea is that you simply have well-defined topological arrangement of domains, which is effectively present.
What does entangled mean?
This is classical. It's not quantum. Now, you might wonder, is there any quantum entanglement? Are these electrons, when you construct a wave function? Of course, that's the next step. We're trying to understand it. The problem is doing the calculation. I mean, it's obvious. It's very trivial to conceptualize what you want to do. You want to do, for example, a DFT over the whole image. Well, unfortunately, it's a very long way to do that. And the best people have been able to do is just one small section of the domain wall. Just one domain wall, a little bit of here. I think that is a calculation, right? In a quantum calculation. So that's the challenge. So
I'm a little confused about this equivocation between atoms and electrons, right? It's talking about here, the electrons are here, that's what's giving you the domain, etc. But for PDF, it's atoms, polarons, or the displacement of the atom as well as the charge and homogeneity, domain, right? So what are we actually looking at? It's ignore atoms except when you didn't want to. Okay.
no, I abstract the atoms out into a polaron. Essentially, all of these objects are not really undressed electrons. You have a space like this, right? Let's suppose we have a Schrödinger, self-Schrödinger equation with a particle in a box of this size. The dynamics is on the 1/52 time scale, right? Depending on the energy you take. Yes, that's an undressed electron. So you have to dress it in order to get any of these. So that basically each one of these electrons should be considered as a dressed electron.
Okay, so atoms are moving too.
Yes, right. They're accompanying.
I also have a technical question about your measurement, how you're switching your measurement noise from the measured noise. Because you have like in one of the
Very good question.
that's Rosen, right? And how this has its own noise and you mentioned like a fast scan or slow
So
scan.
it's actually a simple answer. I mean, that's the first thing that comes to mind. When we actually started doing this, I go, noise specific. Well, yes, but it did not show images. In other words, that's the problem you always have when you're measuring noise. You never know where it comes from. Sample contact, it's somewhere from everywhere. including the amplifier. Here, your amplifier is different here than here. And the spectrum is different in the two places, right? So what I'm saying is that, yes, I cannot tell where is the baseline of my amplifier. And which could be white or not, but it varies. I can identify points on my image which correspond to particular apparent motion or the dynamics of the boron, which I claim are somehow related. But the instrumental noise is always, but hopefully it's the same.
I think it depends on the dynamics, the time springs, you know, if you register in one area, then that means one thing, in other areas.
This is a real, I mean, these are real time, this is a real time loop. So in the sense that one frame per, and one 10 frame per second. So whatever we're seeing is on a particular time window. The noise of the system is assumed not to change as you in that particular area, for example. But that's the point. You could, what you're saying is that, let's suppose this is my object. When my tip comes to here, it'll start becoming noisy. But it's becoming noisy because it's reached the object. Well, it's a bit of a.
It's tricky, it's very, yeah.
But it's a subtle point.
So I'm wondering if you can expand a little bit on the time scales and what's actually happening with this topic. So you have nanoamps on many electrons. And you're imaging kind of single electron sort of, and they're going, you have to go somewhere. And I'm wondering if you can say a little bit more about what this transport, how did it go away? You have to worry about Coulomb gap sort of physics.
All these things are very serious concerns. The first thing you do is to see how much you do. So this 1 nanoamp carrot is actually not heats up the sample by a couple of K in the tip region. So this is scanning across the constant rate. Right? It's sinusoidal. It's just an oscillating. So basically the constant region is separate, but we don't have the. It's metallic. So we're not worried about the Coulomb. At least that's for now.
I mean, just like you know anything about how the electrons are going away as you're one by one and creating some average current from many electron tunneling events. I think is what's happening.
We do know that the next layer is not like that. It's actually doesn't have a structure. Next layer is perfect. It's the top layer, which is by the. I didn't say actually it's purposefully created this structure. It's not. It was not there before. It was laser.
Yeah. Questions? Then let's take this.